Hola, profe.
Hola. Vamos hasta las 8:35 y empezamos. Okay, guys, we're going to start. Remember that we were doing chemical reaction problems. We did one last Monday, and today we're going to do a couple of with combustion. Okay, so I'm going to see two types of problems: one with known fuel, and one with an unknown fuel. Okay. The method to obtain the degrees of freedom and to solve the problem is the same one as with chemical reaction. Okay, it's the same thing. You can use the same three methods: atomic, molecular, or extent of the reaction. Okay, so I'm going to put the presentation. We will begin. Okay. Okay, so the problem for today is right. Is this ethane is born with 50% of excess air. The percentage compression of the ethane is 90%. Of the ethane born, 25% reacts to form CO, or carbon monoxide, and the balance reacts to form carbon dioxide. Calculate the molar composition of the stacked gas on a dry basis and the mole rate of the water to dry stack. Okay, so a couple of things to remember. The first thing is that you need to remember what is complete combustion and what is incomplete combustion. Okay, so remember that in complete combustion, the fuel is oxidized completely to form CO2 and water, or well, depends if it's a hydrocarbon, it's going to be carbon dioxide and water. And if you have an incomplete reaction, you're going to have carbon monoxide and water. Okay. The other thing is the dry basis. Dry basis means that you obtain the percentages of the gases without paying attention to the amount of water. Okay, so that's what we're going to do. Okay, so as with any other problem, the first thing to do is to do a diagram, right? So the diagram, well, first I'm going to put the reactions, right? So ethane is C2H6, right? So if we balance these two reactions, we have C2H6 and C2H6, right? Okay, so the complete combustion, as I told you, is carbon dioxide, and the complete combustion is CO2, right? So this is the complete, and this is the incomplete. Okay, and it's balanced already, right? You have two carbons on the reactants and two carbons on the products, 6 hydrogens and 6 hydrogens on water, and then the oxygen that you have 3.5 or 7 halves of O2, right? That is for the complete reaction, and for the incomplete reaction, it's the same amount of water, 3 molecules of water for each one of ethane, but in this case you obtain 2.5 of oxygen. Okay, so that there we have the reactions are balanced already, right? So then we have to do a diagram, right? So in this diagram, well, I choose already 100 moles of ethane, but you can choose any base that you want, of course, because what we want to obtain is the molar rate, well, the molar composition. That doesn't depend on the amount of, well, depends on the amount of mass or moles and the mole rate, right? So it doesn't matter how much you take care of, how much you use as a base in the inlet of the reactor. And then I wrote down the air stream. Then we're going to have a 50% of air. We don't know the amount of moles right now, so N0, and we know the composition, right? If we don't have any other information, we know that air is composed of 21% in mole of oxygen and 79% in mole of nitrogen, right? So the fractions 20.21 and 0.79. And then in the products, we know that only 90%, well, only 90% of ethane is going to react. So we know that we are going to have a little bit of ethane at the end, right? We're going to have excess air. So we know that we need to have oxygen at the end again, nitrogen too, because well, nitrogen is not going to react at all. And then we're going to have the products, right? One of the products is the carbon monoxide, the other one is carbon dioxide and water. Okay, so we have all known variables, right? From N0 to N6, so 7 known variables, right? Okay, so that's the problem, right? We have the reactions, we have the diagram, and we have a lot of information. Okay, so I'm going to change to another software that find more useful. Okay. So here we have the diagram and the reactions, right? I'm missing here. I'm missing here to write down that the conversion is 90% conversion, and that, well, sorry about it, 24% goes to CO2. To CO, sorry. Okay, so with that we can of course begin, right? So the first thing I'm going to do is to obtain the degrees of freedom, right? Using the atomic balance. Okay, so the number of knowns is 7, right? We have from N0 to N6 right? Then we have I'm going to do the atomic model. Atomic. So I'm going to subtract the number of atomic balance. 3 atomic species, right? So we have 3, that is carbon, hydrogen, oxygen. I'm not counting nitrogen because nitrogen doesn't react, right? Then we have the other equations. I'm going to put it in separate values so you can know which. Okay, I'm going to put other equations. We have 3 different equations. That is the excess air. The excess air, we have the ethane conversion. And we have the CO to CO2 ratio, right? That is the 25% goes to CO, right? And then we have non-reactive species. That is 1, right? In this case, nitrogen. Okay. So if you do the calculation, it's 7 unknowns minus 3 atomic species minus 3 other equations minus 1 non-reactive species. So it's 0, right? So it's okay. So that's what I'm going to do. Okay. So before we do the atomic balance, we can solve a couple of things, right? For example, the excess air. The excess air in the activity that we did, you found how to calculate it, right? So in this case, we're going to obtain the theoretical oxygen that we need, right? So the theoretical oxygen should be equal to the amount of moles of ethane that get into the system, and then by the stoichiometric relation of the complete combustion. Okay, the complete combustion, this one. Okay? That's how we calculate the theoretical oxygen, right? With the complete combustion, and assuming that with the 100% of the fuel is going to react. Okay, so in this case we have for each mole of ethane, we need 3.5 moles of oxygen, right? So this will give us 350 moles of O2. This, remember, is the theoretical value, right? It's not excess just yet. Okay. So to find the excess, I'm going to do an operation using, to obtain N0 with the excess already of air, right? So we can oxygen 0.21 times S0 should equal to the number of moles that we have there over here plus 50%, right? So that is 1.5 times 150 moles of oxygen. So this gives us that N0 it's equal to 2,500 moles of air, right? So now we have our first our first value, right? This one, N0. This with the one of the relations, right? Accessor relation. Okay. Then we can do another thing, that is to obtain the conversion of, well, using the conversion of a thing to know the amount of a thing that we have at the end, right? So to calculate N1. So N1 is going to be equal to the amount that didn't react, right? If we have a 90% conversion, then 60% react. And the fraction for that is 0.1 didn't react times the 100 moles that we have at the beginning, right? And this is, of course, 10 moles of C2H6 in the gas stack, right? Okay, and the other thing that we can do before is with the other equation is the using the ratio, right? The 25% conversion. Okay, so let me put a box this one so we know that we have it already. Okay, so then we do using the conversion, we can calculate N4, right? That is the CO. We have that 25% of the ethane that reacted goes to CO, to carbon monoxide. Okay, so the carbon monoxide at the end, N4, should be the 25%, right, or 0.25 of the thing that reacted, right? The thing that reacted is 90% conversion times 100 is 90 moles of the thing that reacted, right? Okay. This, well, we use the stoichiometry of the reaction, right? We have that for each 1 mole of ethane, 2 moles of CO2 are created, right? So we write down that exactly. 1 mole of C2H6 produces 2 moles of CO, right, of carbon monoxide. And that gives us that N4, it's equal to 45 moles of CO, right? Okay. And then we can, using, for example, the nitrogen balance, we know that we have a non-reactive species over here, a non-reactive species, so we can calculate the amount of nitrogen that goes out, right? Because nitrogen that gets into the reactor is the same amount that goes out of the reactor, right? So N3, that is nitrogen, is going to be equal to the amount of nitrogen that we have at the beginning, right? That is 0.79, that is 79%, times the inlet, the N0, right? That we calculated already as 2,500 moles of air, right? Okay, so this gives us that N3, the amount of nitrogen, is 1,975 moles of N2. Right, so we have now 4 values, 4 of the 7 values that we needed, right? I'm going to change color for the next part so you can see it differently. Now we're going to calculate, using the atomic balance, we're going to calculate the other variables, okay, that we're missing. Let us show the carbon dioxide, water, and oxygen, okay? So we're going to do an atomic balance. Atomic balance for carbon. Okay, in this case, and as always with atomic balances, the output is equal to the input, right? Okay, so we have the inlet. The inlet is going to be, of course, the 100 moles of ethane multiplied by the stoichiometric relation, right? Okay, so here we're going to have the 100 moles of ethane, C2H6, and we have the relation, right? Again, I have a problem over here with my tablet. Yep. Okay, so the 100 moles times the stoichiometry of that particular. So for each mole of ethane, we have 2 moles of carbon, right? Of carbon atoms. And this is equal to the amount of moles that we have at the end of ethane. We calculated that there were 10 moles of ethane. And again, the relation is 1 to 1, right? And then we have the number of moles of carbon monoxide that we have already. Carbon monoxide is 45 moles of carbon monoxide, right? And the relation of carbon monoxide and carbon is 1 to 1. And of course, we have the amount of moles of of CO2 that we have at the end that we don't know right now, right? It's N5. So N5, and we're going to again to multiply it by the relation. For each 1 mole of carbon dioxide, we have 1 mole of carbon, and that's it, right? With this equation, we only have one unknown variable, that is N5, right? So we can solve this problem, right? So doing the algebra, we obtain that N5 is equal to 135 moles of CO2. So we're almost done. Now we're going to have an atomic balance for hydrogen. Again, output is equal to input, as usual. So in this case, the inlet is just the hydrogen that goes in with the ethane. So again, 100 moles of ethane. And then with the stoichiometric relation, right, for each mole of C2H6, we have 6 moles of atomic hydrogen, right? And then we look for the other components that have hydrogen, in this case, the thing that didn't react, and the water. Okay, so the thing that didn't react is 10 moles of ethane, and again for the relation 1 to 6, and then plus the value that we don't know for water, that it's N4, right? And the relation for each molecule of water, we have 2 atoms of hydrogen. Okay, again we only have one value, well, one unknown variable in this particular equation, and then with that we obtain that the N4, that is the amount of water, it's going to be equal to 270 moles of water. Okay, and the only part that we're missing is the oxygen at the end, right? So we do an atomic balance for oxygen. Okay, again, input is equal to output. Okay, so the input, we know that is the 21%, right, of the gas current, or of the air current, that is 2,500 moles. This is the amount of moles of oxygen, right? Moles of oxygen. And then for the stoichiometric relation, for each mole of O2, we have 2 moles of oxygen. That should be equal to the output, right? The output, we have a couple of different components that have oxygen. Well, oxygen, of course, carbon monoxide, carbon dioxide, and water. But we have all those values, right? So the only one that we're missing is N2. So N2 is the moles of oxygen, and again for the relation, for each molecule of oxygen, we have 2 atoms of oxygen, and then we add all the other components, right? N4, that is for the carbon monoxide, we have 45 moles of carbon monoxide, and for each carbon monoxide we have 1 oxygen. Then we add the carbon dioxide, that is N5, that is 135 moles of carbon dioxide. For each mole of carbon dioxide we have 2 moles of oxygen. And the last one is the water, that is N6. Sorry. Yeah, here I have a mistake in the writing. I write it down N4 and it's N6. Sorry. So N6 is the water, and we have 270 moles of H2O, and each mole of H2O has 1 atom of oxygen. And that's it, right? We have over here, again, the only known variable is N2. If we solve the algebra to the calculations, we obtain that the oxygen at the end is 232 moles of O2. Right, this is equal to N2. Okay, and we finish the balance. Okay, any questions for this particular problem?
Yes, I have one. In the middle part, where you have 0.21 and 0 equals 1.5.
This one?
Yes.
Okay, yeah.
Where did you get the 1.5 from?
The 1.5 is the excess air, right? We have 50% of excess.
Yes.
So we know that the theoretical value is 350 moles of oxygen, right? We need to put 50% extra. So that's why I'm adding this 0.5, right?
So there is 150% of air in total?
Yeah, because it's 50% of excess, right?
Oh, okay. And the one in the bottom?
The one in the bottom over here, the atomic balance of oxygen?
No, the one that says N1 equals 0.1 times 100 C2H.
Okay. N1 is the number of moles of ethane, right? At the outlet of the reactor, yes. Of the combustor, this case. Okay, so the 0.1 is the amount that didn't react, right? 10% didn't react. We have a conversion of 90%, right?
Okay. Okay.
So 10% didn't react of ethane.
All right.
So that's why we are multiplying 0.1 that didn't react for the amount that was in the inlet, 100 moles, and that gives us the 10 moles at the end.
Okay, thank you.
Yep. Any other questions, guys? Please, if you have questions in the middle of the problem, it's fine, right? Okay, so unmute your microphone and ask the question, okay? So we can solve the questions while we are working on the problem. Okay. Yeah.
Why do we multiply 0.21 on the atomic balance?
Which balance? This one, in the atomic balance of oxygen?
Yes.
Because here we're calculating, let me put another color to put it down. Okay, so here the 0.21 times the 2,500 moles is to obtain the moles of oxygen, right? Because 2,500 is the amount of air, right? But air has oxygen and nitrogen.
Mm-hmm.
Okay, so here we're doing an atomic balance of only oxygen. So we need to calculate the amount of oxygen, that is the 21% of the inlet of air.
Okay.
Yep.
Thanks.
You're welcome.
Other question, teacher.
Yes.
How does it depends in the atomic balances that we put output equals to input or input equals to output?
It doesn't matter. It's the same thing. It doesn't matter in the order that you put it, but it's as long as you have all that was the input or the inlet or the outlet in one side and the other side the other one, it's fine.
Okay, thanks.
You're going to find the same equation, right?
Mm. Okay.
Yeah, it doesn't matter at all. Okay, so any other questions for this problem, guys?
Teacher, I don't understand N4. Like, why you multiply 0.25.
0.25,
Yeah, in N4, yeah.
Okay, in N4, yes. Okay, so N4, if you follow the diagram, N4 is the amount of carbon monoxide, right? So here in the problem, we had that 25% of the ethane that reacted goes to CO, right?
Okay.
So that is this 25%, this 0.25, right? 25% of the ethane that reacted, in this case 90 moles, because only 90% was the conversion, right? So
Okay.
25 is because the problem said that 25% goes to CO.
Okay.
Right?
Yeah.
90 is the amount of ethane that reacted. Yes.
In N3, I don't get why you would multiply with how you did it, because it's before the reaction, not after.
Okay, yeah. But remember that the nitrogen that is N3, right? Nitrogen that is N3 doesn't react, right? It only goes into the reactor, but it doesn't react.
Okay, thank you.
So it should be the inlet is equal to the outlet, right? To find the nitrogen.
Thank you.
Any other questions, guys?
Yes, the one you explained to me, I know where the 1.5 came from, but I still don't understand the logic of the equality.
Okay, so here what I'm doing is the balance of oxygen, right? So I calculated the theoretical oxygen, that is this one, right? That is the stoichiometric amount of oxygen that we need for that particular reaction to be completed, right? So 350 moles of oxygen. Right?
Yes. Okay. Yes.
So then to find N0, because oxygen goes into N0, right?
It's just 1.21% of the total 150%.
No. This is the inlet, right? 0.21% is the oxygen that goes in, right?
Yes.
0.21 times N0 is the oxygen that you are putting in the inlet, right?
Yes.
Okay, so that is why we put 0.21 N0, right?
Yes.
And then the 1.5 times 350 moles is the excess. This gives us the 50% of excess.
Okay.
Right?
Yes.
And that's it, right? If you have, for example, 5% of excess, you will have multiplied this by 1.05, right?
Yes.
So,
okay, so the 350 is our 100.
Yeah, exactly. Is the stoichiometric amount, right?
Okay. Thank you.
You're welcome. Any other questions before I go to the next page so we can do the final part of the problem?
No.
Okay. So let me change page. Okay, so here the only thing I'm going to do is a couple of calculations to obtain the values that the problem asked for, right? The problem asks for the molar composition of the stacked gas. Okay, so we found that already, right? We have that N1 is equal to 10 moles of C2H6 of ethane. N2 is equal to 232 moles of oxygen. N3 is equal to 1,974 moles of nitrogen. N4 is equal to 45 moles of CO, carbon monoxide, and N5 is equal to 135 moles of CO2, right? These are the dry gases, right? Without taking into consideration the water. So this adds to 2,396 moles of dry gas, right? Of dry gas. And we have, well, N6, that is the water, right? Water is 270 moles of water. Okay, so if you add up all that, it's 2,666 moles of wet gas or total of gas, right? Okay, so that is the one particularity, and then and the other it tells us that we needed to obtain the fractions, right? The gas fraction. So in this case, y1, that is the gas fraction of the component 1, and so on, right? So we have in dry basis, it asks us for, right? So y1 will be 10 moles, that is 10 moles of ethane divided by the amount of dry gas, right? And this will be 0.0417. Sorry, 417. Y2 will be the one for oxygen, that is 232 divided by the total amount of dry gas, that is 0.097. Y3 will be the amount of nitrogen, the concentration of nitrogen in the dry gas. That is the highest amount, right? Because we have a lot of nitrogen in air. So this is 0.824. This is a common value. Around 80% of the flue gases are of nitrogen, because we have a lot of gases in there, a lot of nitrogen, sorry, in there. And again, for the carbon monoxide, we do 45 divided by the total amount of dry gases, so 0.19. And the one for carbon dioxide, that is 135, again divided by the total amount of dry gases, and this gives us 0.0. I'm sorry.
Teacher,
Yes.
where did you get the 2,666 from?
I add 2,396 of the dry gases plus the 270 of the water.
Ah, okay, thank you.
Because water goes in vapor phase, so it's a gas too. But if you remember the activity that you did about combustion, when you do an ORSAT analysis, you can't find the amount of water because the technique is dissolving gases in water. So you can find the amount of water. The only way to obtain the amount of water is doing a mass balance like this one. Okay, and the last part is the ratio of water to dry stack gas, right? Ratio of water to dry gas. So the amount of gas, of water, 270 moles of water to the dry gas, right? So 2,296 moles of dry gas. And that gives us that we have 0.113 moles of water for each mole of dry gas. And that's it. That was this particular problem, right? So we finished already all the questions that were asked and all the balance, okay? Most of the problems about combustions, we have either this type where you have the, for example, the inlet, but you don't know the outlet, or the other way around, you know the outlet, but you don't know the inlet, or you're missing a couple of things on the inlet. So that's the last problem that we're going to see. Okay.
Teacher, I have a doubt.
Yeah, of course.
Why did you divide 217 mole of water over 2,396 instead of 2,666?
Okay, because the problem, it says that we need the dry basis, sorry, the mole ratio of water, right, to dry gases, right, to dry gases, dry stack gas, okay? So the dry stack gas is, of course, without taking into consideration the water, right? So that's why we did these two additions, right? This one, 2,396 mole, is just of the dry gases, right?
Yes.
Without taking into consideration the water. So that's why we had the ratio of water to dry gases, right? So that's why I used that one, the dry gas, the total amount of dry gases.
Okay.
Yep.
Yep.
Any other questions of this final stage of the problem? Okay, so I'm going to do next then the other type of problem. So we did the solution already. So this exercise says hydrocarbon gas is bond with air, and the dry basis product gas composition is 1.5 mole% of carbon monoxide, 6% of carbon dioxide, 8.2% of oxygen, and 84.3% of nitrogen. There is no atomic oxygen in the fuel. Calculate the ratio of hydrogen to carbon in the fuel gas and speculate on what the fuel might be. Then calculate the percent excess air fed to the reactor, right? Okay. So in this case, we have the other way around, right? We have the outlet, but we don't know much about the inlet. Okay. So use a couple of minutes, 5 minutes, to draw the diagram that you think you should have, right? And try to propose the reactions that we need. Okay. If you have any questions, of course, let me know. Okay, guys, do you have any questions about how to propose the diagram? Well, the outlet and that kind of thing.
Teacher, the hydrocarbon, it's something with CH that has C to the N and H to the 2N or something?
Yeah, well, you know that it's a hydrocarbon, so it has to have carbon and hydrogen, right?
Yes.
It says explicitly that you don't have any atomic oxygen in the fuel, right?
Okay.
Over here, right? Okay, so you know that fuel should have only carbon and hydrogen.
Okay.
So that's a way to propose the inlet, right? Any other questions about the diagram? Or the exercise in particular? Okay, so what you should have proposed more or less is the diagram that you see here, right? We know that we're going to burn fuel with air, right? So we're going to have an inlet of air. And if we have an inlet of air, of course, we know that it's going to be 25.21 of oxygen and 0.29% of nitrogen, right? And then we have the fuel. The fuel, it says there is a hydrocarbon, so it means that it has at least carbon and hydrogen. And in this point, it says explicitly that that particular fuel doesn't have any oxygen, right? There is no atomic oxygen in the fuel. Okay, so we can propose an inlet of carbon, okay, an inlet with a number of moles of carbon and with an amount of moles of hydrogen that we don't know. Okay, we don't need the actual component to do this problem, because we know the reactions for carbon and the reactions for hydrogen, the combustion, well, the combustion reactions for carbon and hydrogen. Okay, and then in the outlet, it's telling us that the dry basis, right, without water, it has this percentage, right? So we can propose that the gas stack, it's formed of these components: carbon monoxide that we have 1.5, so 0.015 in fraction, 0.06 in fraction of CO2, 0.08 fraction of oxygen, and 0.843 of nitrogen, right? And we can propose that, of course, if you have hydrogen, in this fuel, of course, water should be formed, right? So we need to add an amount of water that we don't know right now. Okay. And again, I propose.
Why do we add water?
Because we have hydrogen on the fuel, right? So the combustion of a fuel that has hydrogen is going to produce water always. Okay. So we know that we should have water at the end. Okay. And we know that this was in dry basis, so we know that those fractions were without water. Okay. And then we propose, well, in this case, I propose 100 moles of dry gas. It can be again whatever, right? I propose these moles because is the outlet, well, is the stream that we know that we have more information about, right? We have all the percentages of the gases, and we're just missing a number of moles of water. Okay. And then we need of course, we need the reactions, right, to see how the reactions behave, and then what are the stoichiometric relations and so on. So the reactions that we can propose is, of course, the carbon and hydrogen that are oxidized with oxygen, right? So those reactions are this one, right? We have the complete combustion of carbon, that is carbon plus oxygen that goes to CO2. And then the incomplete combustion of carbon, that is 2 moles of carbon reacts with 1 mole of oxygen to form 2 moles of carbon monoxide. And then we have the oxidation or the combustion of hydrogen. That is 4 moles, well, 4 atoms of hydrogen react with 1 atom of oxygen to form 2 molecules of water, right? So now we have all the information that we need, right? So this problem, you have to do something very similar to what we have done all this time, right? To propose the degrees of freedom, to write out the balances that you have. For example, if you do atomic, you're going to have carbon, hydrogen, and oxygen. Nitrogen, you again know that it's not going to react at all, right? And so on, right? So what I'm going to do is some teams, right? We're going to do some breakout rooms so you can work in teams, and I'm going to, of course, be monitoring you guys. If you have any questions in the software, in the Zoom software, you can ask a question and so on. Okay. So I'm going to do teams of 3. I'm going to be moving through the different breakout rooms. Okay. Any questions before we begin? Okay, so I'm going to do 6 rooms between 2 and 3 participants. Okay, see you in a bit inside of those groups.
por especies atómicas. Porque para sacar el oxígeno teórico necesitamos como algo que entre, ¿no?
Bueno, si quieres podemos hacer, ¿cómo se llama? Podemos empezar por los balances y ya, ¿no? Si quieres.
Sí. ¿Cuáles balances?
O sea, atómicos de cada uno de las salidas para ver cuánto entró. O sea, con las reacciones, ¿no?
Ajá, y así podemos sacar el NH, yo creo, y el NC.
Ajá.
Y
Ajá.
ya podemos sacar lo demás.
Después, ajá, exacto.
Chicos, recuerden que el nitrógeno no reacciona, ¿no?
No, sí.
Entonces, lo primero que pueden hacer, así como lo hicimos en el otro problema, es resolver primero las cosas que se puedan resolver. Entonces, por ejemplo, el nitrógeno que no va a entrar entre los balances atómicos,
Ajá.
pueden hacer ese balance, hacen el balance de nitrógeno, y con eso, ¿qué obtendrían? Si hacen el balance
El Na, ¿no?
obtienen Na, ¿no? Obtienen 1 moles de aire directo.
Ok.
Y ya de ahí se pueden, dado que no hay más información, ahí sí ya se tendrían que seguir ya sea a balances atómicos, moleculares o de avance de reacción, ¿no?
Ok, sí.
Bueno.
A 100 por .82. Déjame voy por mi calculadora.
¿Todo bien por aquí, Ricardo?
¿Mandé, profe?
¿Que todo bien por aquí?
Pues ahorita sí. Gracias.
Entonces es .82%.
De atómicos son 1, 2. ¿También se cuenta el N2? Sí, ¿verdad?
Sí.
1, 2, 3, 4.
No, el N2 no se cuenta.
¿No?
¿Para
¿Seguro?
los atómicos?
Ajá.
No,
Para el
porque,
atómico.
porque es una especie que no reacciona.
Ah, ese sería el último, ¿no? El de
Ajá.
Ok.
no sé qué species.
Non-reactive.
Non-reactive, eso. Perdón. Non-reactive species. Entonces.
Ok, entonces
Empiecen por
serían
eso.
1, 2, 1, 2, 3, 4, ¿no?
Sí,
4. 4. Y el número, no, pero... ¿Sí?
A ver.
¿Mande?
No. Estoy viendo.
Menos 4 atomic species.
Claro.
Y luego, other equations. No, ¿verdad?
Other equations, pues no tenemos ninguna relación, ¿o sí?
No.
No hay relaciones.
Cero.
¿Alguna duda?
Y non-reactive tampoco, ¿no?
No, profe, hasta ahorita estamos haciendo...
Yo sí tengo una duda. No, ahí quizá. Profe, ¿la composición del aire siempre va a ser la misma? ¿O tenemos que asumir que cuando haya combustión siempre va a haber una, participación del aire?
Bueno, si no te dicen o sea, si no te dan especificaciones de la entrada de este caso del oxidante, lo que te dicen es aire, así en general, siempre es 21% molar de oxígeno, 79% molar de nitrógeno.
Ok.
Si no te dicen nada diferente.
Ok. Y aquí como dice que tenemos... Bueno, o sea, el problema no menciona que haya intervención del aire, pero como es una combustión, lo asumimos. O sea, es como...
Claro. Sí, si no metes aire, pues no hay manera de que se queme, ¿no?
Ajá, de que ocurra.
No
Ok.
tienes un oxidante, no metes
Sí.
oxígeno.
Ok, ya. Sí, es mi duda. Gracias.
Profe, yo también, I have another question. If we always have to assume that we will have a dry basis from the combustion.
No, the problem usually tells you Okay, it's the common thing is to obtain a dry basis gas stack because if you remember the ORSAT, the ORSAT method to obtain the percentages uses water to dissolve the gases, so you can obtain the amount of water on it. So usually it's dry basis gases, but it doesn't have to be. Okay.
You.
Welcome. See you in a bit.
Okay. ¿En qué estamos?
En degrees of freedom. Ya.
Hi, teacher.
Hello. How are you guys?
Hi, teacher.
Any doubts, questions, or something?
Yes.
Let me know.
Is it correct to say that for carbon it's 7.5 mole?
But why?
Because according to what you said, that inputs equal outputs, I made an equation that says that the mole of carbon equals 100 times the fraction of CO, that is 0.015,
It is correct.
times 1/1, because one carbon in one, there is one carbon in one CO, plus 100 times 0.06 times 1/1, and that equals 7.5.
Exactly. Yep.
Yeah.
Yeah, it's the atomic balance of carbon, right?
Yeah. But for O2, I don't know how to do it with oxygen, because
well, remember that, for example, in the oxygen is going to go with air, right?
Yeah.
Is there any way to obtain the amount of moles of air without using the oxygen?
The theoretical value?
No, well, not exactly. You know the amount of nitrogen, right, on your outlet?
Yeah.
Right, that is 84.3 moles, right?
Yep.
Does nitrogen react?
No.
So the nitrogen should be the same as the inlet, right?
Yes.
Okay, so now if you know that the amount of nitrogen at the inlet is 84.3 moles because it doesn't change, right? It doesn't react. Then you can calculate NA, right? That is the number of moles of air.
Okay.
Correct?
Yep.
Okay, and with that you solve that part, right? You know the amount of oxygen.
And if it says that it's 0.21 mole of oxygen in the concentration of air, I have to divide it over that or multiply it.
Well, in this case, would you do for example, do a nitrogen balance, right? The nitrogen that goes in, it should be 0.79 times Na, right?
Okay, yeah.
That should be equal to 100 times 0.843, right?
That is equal
solve Na, right?
Okay.
Let me go to another room that somebody asked a question.
Okay.
Como la primera ecuación que tiene O2 es la primera, entonces sería un mol de carbono.
¿El segundo de oxígeno?
Ajá, o sea, un mol de carbono de la primera ecuación es igual a 2 moles de O2, ¿no?
Guys, you asked a question, right?
Yes, teacher.
¿Le podemos preguntar en español?
Está bien.
O sea, tuvimos el Na por balance por especie y ahorita para obtener los demás resultados, o sea, para obtener el porcentaje de exceso de aire, o sea, tenemos que hacerle como en el pasado, ¿no? Que hacer como balance atómico de cada uno para obtener los moles.
Sí, o sea, primero lo que tienes que hacer primerito es obtener los resultados, o sea, el balance, ¿no? Entonces, ya que obtengas el balance de cada una de tus incógnitas, de NC, NH, NA y NW, ya con eso, ya puedes entonces, ahora sí, hacer el porcentaje de exceso. ¿Ok? Para hacer el porcentaje de exceso, hay que tomar en cuenta la combustión completa de los elementos que tengas, ¿no? Y con eso sacas el oxígeno teórico. Y con el oxígeno teórico y el oxígeno alimentado, puedes obtener el porcentaje de exceso.
Ok. Pero sí se sacan los moles, ¿no? De cada uno.
Sí, primero necesitas resolver los moles de cada cosa.
Ok. Y para hacer los moles, hace cuenta, multiplicaría o sea, me baso en la reacción, ¿no? Por ejemplo, para sacar 2 moles de dióxido de oxígeno, así se dice, no, que ya de O2,
Ajá, de
tendría
oxígeno.
que multiplicar 0.060 por 100.
¿Por qué punto de 60%? Ese es para el... Ah, ok, es que a ver, ahí te está haciendo por el lado largo.
Ajá.
Porque con el nitrógeno que tienes, puedes calcular la corriente de oxígeno de entrada, ¿no?
Ujú.
Entonces, ya sabes, con ese, o sea, con el nitrógeno puedes calcular Na,
Ajá.
¿cierto?
Sí.
Sí.
Entonces, ya que calculas Na, pues ahora sí haces los balances atómicos, tanto para carbono, para oxígeno, para hidrógeno.
Ok.
Para el del carbón, para si haces el balance atómico del carbono, pues del lado de los productos ya conoces todas las cosas que tienen carbono, ¿no? Ya conoces cuánto CO hay, cuánto monóxido, cuánto dióxido de carbono hay, ¿no? Entonces ya con eso calculas NC, ¿no? Calculas el número de átomos de carbono,
Sí, sí, sí.
¿cierto?
Ujú.
Y entonces ya luego haces el del oxígeno, y luego haces el del hidrógeno y ya calculas pues cada cosa, ¿no?
Ok.
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 Ya vengo.
Ok, gracias.
Profe.
Bien por, o sea,
De CO2.
bueno, 6 moles de CO2.
Ah, pero pues te da negativo, ¿no? Según yo.
Mm,
O sea,
sí,
si
sí.
sacas NG, por eso dudo si es positivo.
¿Pero por qué sería negativo?
Ay, no sé, ¿para qué te di?
¿Qué podría ser negativo?
Ah, hola, profe. Es que no, estamos un poco perdidos.
A ver, ¿en qué parte?
O sea, se supone que sacamos los moles de nitrógeno, o sea, ponemos Na por 0.79 es igual a 100 por 0.843, ¿no? Y despejamos a Na, despejamos y nos da los moles o sea, el Na, ¿no?
Ajá, y está correcto.
Y eso lo multiplicamos por 0.21 para que nos dé los moles de oxígeno.
Sí.
Y después hacemos el balance con la primera reacción, la de C más O2 es igual a CO2.
No.
Ponemos NC, NC más los moles de O2 que sacamos ahorita es igual a los 6 moles de CO2, ¿no?
No lo puedes hacer así, ¿no?
¿No? Ah, ¿por
No,
qué no se puede?
porque recuerda que también estás produciendo dióxido de carbono y monóxido de carbono.
Ok.
Entonces, ahí lo que les conviene hacer es utilizar especies atómicas. Entonces, todo el carbón que entra es igual a todo el carbón que sale.
Okay.
Entonces, todo el carbón que entra, pues NC, ¿no?
Ajá, NC.
Y eso tiene que ser igual al carbón que sale. El carbón que sale en monóxido de carbono y dióxido de carbono, ¿no?
Ok.
Y entonces, si hacen el balance, pues ahí ya tienen 100 moles de gas que tiene 0.015 de CO y 0.06 de CO2, ¿no?
Ajá.
Entonces, si hacen el balance, con eso obtienen NC.
Ok.
¿No?
O sea, entonces tendremos que poner...
NC es igual a todo el carbono que sale.
Exacto, utilizando sus relaciones estequiométricas entre el compuesto y el átomo, ¿no?
Ah, ok.
Son 1 a 1, ¿no? Okay. tanto monóxido de carbono como dióxido de carbono pues, tienen un átomo de carbono, ¿no?
Ujú.
Ujú.
Pero por ejemplo, no, ya vi.
Ujú.
O sea, entonces literal ponemos NC es igual a puntos, punto 06 y su relación, que es 1 a 1, ¿no?
Ajá.
Y luego más CO, o sea, un punto,
Pues te
punto
falta
015.
por la cantidad de moles de esa corriente, ¿no?
Ok, o sea, es los moles por el porciento, ¿no? Sí.
Entonces sería 100 por punto 015 por la relación estequiométrica del CO, que es 1 a 1, ¿no?
Ok,
Luego le
ajá,
sumas lo demás, pues el 100 por punto 06 de CO2 por la relación estequiométrica, que es 1 a 1.
ok.
¿Y eso cuánto
Y
es?
ya nos da la fracción de,
La cantidad de
a
moles.
ver, la cantidad de moles, sí, ¿verdad? A ver, entonces. Ok,
Y
gracias, profe.
entonces lo mismo hacen después pues, para las 3 especies atómicas, ¿no? Hacen balance de oxígeno, digo, hacen balance de carbono, hacen balance de oxígeno, hacen balance de hidrógeno, ¿no?
Sí,
Bueno,
ok, gracias, profe.
Ujú.
Hello,
Y
guys.
su relación estequiométrica es
1 a 1.
igual 1 a 1. Ya está el profe aquí. Teníamos una pregunta, ¿no?
Sí.
Lo de... sí, lo de degrees of freedom. Profe, it's possible that if we have in the degrees of freedom -1, we can start with that one, or we have to search for another one that is 0 or 1.
And if it's -1, it's over-specified, right?
So
But
we
it
did it.
shouldn't give you that. How did you calculate it, the degrees of freedom?
Because we have 4 unknown variables.
Yep.
No? Yes?
Yes.
Then we have 4 molecular species, well, atomic species.
Okay.
And we have 1 non-reactive, that is the nitrogen.
Okay, so that's 0, right?
No, because it
No.
was 4 minus 4 minus 1.
Okay, sorry. In the independent atomic species, what did you count as atomic species?
The independent atomic species, we count the carbon, the hydrogen, the nitrogen, and the oxygen.
Okay.
Those 4.
Nitrogen is not an independent. Is not a atomic species that is going to react, right?
Yeah, right.
If you see your reactions, you don't have nitrogen, right? As a reactant.
So it doesn't react. Okay.
So it
So
should be 3 species, right?
and now we have 0. Yay.
That one.
Okay, thank you, teacher.
So no, we only have to count the species that react when we do. Okay, thank you.
Yes.
Okay.
Yeah, that's all.
Okay, see you in a bit.
Thank you. Bye.
Hello. Are you there, guys?
Yeah, I'm here.
Okay. So,
Teacher,
yep.
do you have the answers?
Yes.
Is it correct that NW equals 44.814?
And where is it on? NW, how much is it?
44.814.
Nope.
No?
Way too much. No, because how did you obtain that value?
First, I calculate the mole for air, that is 106.70. And that with that value, I substituted in the equation for O2, and I multiply it times 0.21, and that is 22 point something. And then for water, I have two equations that is 106.70 times 0.21, that is the fraction mole of O2, times 2/1, because there is 2 mole of O in O2, and that is equal to the fraction of water times 1/1.
Yes,
And that is 44.814.
Yeah, but you're missing a lot of things there, because what you're doing there is it's atomic balance of oxygen, right?
Yes.
So you need to take into consideration all the other things that have oxygen. For example, carbon dioxide has oxygen, carbon dioxide has oxygen, and oxygen has oxygen, right?
Yes.
So you need to plug in all those data, right? You're going to have the 0.21 that you save times Na times 2, right? And that should be equal to the number of moles of water, and then all the other components that have oxygen, right?
Okay. Then I have to add the 0.06 of the CO2 and the 0.082 of O2 in the product.
Well, yeah, but remember that you need to multiply it by the amount of moles, right, of 100.
Yeah. Okay.
And the relation, right? If it's carbon monoxide, you only have 1 atom of oxygen, but if you have carbon dioxide, you have 2, and if you have oxygen, you have 2, right?
Okay.
So yeah, right.
Do you need to solve it, or we have to? After this, are you going to solve the problem?
Yeah, well, I would like for you to reach for the balances, and then I was going to do the last part, that is the what kind of fuel it is and kind of things.
Okay. How much time is left? Sorry.
Like 5 minutes.
Okay.
Yep.
Thank you.
You're welcome.
O sea, digo, por cada 2 moléculas de CO se ocupa una de oxígeno, que eso equivale según yo, o bueno, sí, que eso según yo equivale como a 2 O, por así decirlo.
Hello, guys.
Hi.
Sorry? Any questions?
Sí tenemos una, profe, pero es que, o sea, no entiendo, o sea, no entendemos bien, o sea, nosotros lo estábamos haciendo así, o sea, pusimos oxígeno y, por ejemplo, hicimos como 2 veces por 0.21 por la Na, porque tenemos 2 oxígenos, o sea, lo que...
Lo estaba multiplicando por el numerito que tiene al lado.
Ajá, o sea, las 2 veces el oxígeno.
Esa es la relación, ¿no? Por cada molécula de O2 hay 2 átomos de O2, ¿no?
Ajá, exacto. Y de salida, por ejemplo, no sé, con el CO, nada más era 100 por 0.015 por 1, porque nada más tenemos un oxígeno.
Exacto.
Pero tenemos duda, o sea, de los que... O sea, como de las reacciones, ¿eso cómo afecta? O sea...
Ahorita para el balance que estás haciendo no te afecta en nada.
No, ¿verdad? No las tomo en cuenta.
No, solo la estequiometría de los compuestos, ¿no? ¿Qué tantos oxígenos, qué tantos tiene cada uno?
Ah, ok. ¿Y ya las reacciones cuándo afectan?
Esas las tienen que usar para calcular, por ejemplo, el porcentaje de exceso de oxígeno.
Ah, ok, va. Vale.
Pero si en este momento, o sea, si ya calcularon Na, que ya lo deben de haber calculado con el nitrógeno, pues ahora hacen balances de carbono, hidrógeno y de oxígeno y obtienen pues NC, NH y NW, ¿no?
Sí.
El agua, el NW, déjenlo hasta el final, porque como el agua tiene oxígeno también, primero tienen que saber qué onda con el oxígeno.
Ah, sí, en esa se tendría como que dividir los moles en 2 partes o algo así.
No.
O como, o sea, o multiplicaríamos como, no sé, o sea, nos salió como, no sé.
Pero tú vas a hacer tu balance de hidrógeno, o sea, digamos, con el balance de oxígeno, vas a obtener la cantidad de agua que te falta. ¿Sí? Porque si te fijas, en la entrada no hay nada de oxígeno, digamos, en el combustible no hay nada de oxígeno. Entonces todo el oxígeno viene en el aire, ¿no?
Ajá.
Y luego se va a ir a monóxido de carbono, dióxido de carbono, oxígeno y agua, ¿no? Y el único que conoces de ahí, pues es el agua. Entonces de ahí vas a obtener NW. Y del balance de hidrógeno vas a obtener NH.
El balance de hidrógeno, voy a obtener NH. Ajá.
O sea,
Pero entonces sí tendremos que empezar por NW, ¿no?
no, o sea, es mejor empezar por NC, luego NO y luego, o sea, digo, por el balance de carbono, luego por el de
carbono.
hidrógeno.
Ajá, pero por ejemplo, o sea, para obtener NW usaríamos el de oxígeno, ¿no?
Ajá, exacto.
Ah, ok.
¿Sí?
Ok, sí.
Muy bien.
Sí, creo que sí.
Ya en unos 3 minutos le paro porque si no, no
sí.
tengo que acabar de resolver un problema,
Sí.
resolver el problema, ¿no?
Ok.
Sí, vale. Gracias.
Nada.
Entonces ya, sí, estamos bien, estamos bien.
Ajá, entonces,
Pero ya lo entendí, o sea, ya lo entendí, sí, sí.
Welcome back, guys.
Ujú.
I'm going to show you how to solve the problem and the other couple of things, okay? Because if not, we're not going to finish on time. Okay, so we have this screen over here, okay? And okay, so the degrees of freedom, I think everybody calculated correctly, right? If we do atomic balances, we have 4 unknowns that were NH, NC, NA, and NW, right? Then 3 atomic balances, the ones that react, right? So carbon, hydrogen, and oxygen, and 1 balance for the nitrogen that it doesn't react, right? So 0 degrees of freedom. Okay, so the first thing to do is, like we did in the first problem of today, is to solve the things that we can solve before doing the balances. In this case, we can do the nitrogen balance. Okay, so the nitrogen balance, we know that there is composed of fraction of 0.79 of nitrogen times the number of moles of air, in this case Na, and we know it's not going to react, so it's going to be the inlet is going to be equal to the outlet. Okay, so the outlet, we know the percentage, well, the fraction 0.843, right, and the number of moles of the gas stack, that is 100. So with that, we obtain that the number of moles of air is 106.7 moles, right? And that's it. That's the only thing that we can do before doing the balance. In this case, atomic balance is the best one because we'll have exactly atomic species at the beginning, right? So the balance of carbon, we know that the carbon that gets into the system is just the number of moles of carbon in the fuel, and then that should be equal to the outlet, right? The outlet is 100 moles of the gas stack times 0.015 for the CO, and then the stoichiometric relation, that is for each mole of CO, we have 1 mole of carbon, and the same thing for the carbon dioxide. In this case, 0.06 is the fraction, 100 moles of gas stack, and again the relation is 1:1. So with that, we obtain that the number of moles of carbon should be in the fuel should be 7.5. Then, because we have, if you see in the atomic balance of hydrogen, for example, we're going to have two different values, two known that we don't know, right? We have NH because water has a hydrogen, and we have NW, that is the water, right? So it's not good to begin with that one, with atomic balance of hydrogen. It's better to start with the balance of oxygen, that the only known that we have for oxygen, for the balance of oxygen, is the amount of water, right? So again, this 0.21 is the fraction of oxygen in the air. Na is the number of moles of air, and 2 is the relation, right? 2 atoms of oxygen per molecule of oxygen, of molecular oxygen. And that should be equal to the components that have oxygen, in this case water, times the relation, because water has 1 oxygen, and then plus all the gases in the gas tank that has oxygen. In this case, we're going to multiply 100, that is the amount of moles of the gas tank, and then for each one, for CO, for carbon monoxide, carbon dioxide, and oxygen, right? So the fraction, 0.015, 0.06, and 0.082. And then for the stoichiometric relation of oxygen to that molecule, in carbon monoxide 1, in carbon dioxide 2, and in oxygen 2. And with that, the only value that we don't know is NW, because Na we found that already, right? So with that, we substitute all the data, and we find that the number of moles of water should be 14.9 moles of water. Okay? And then the last balance that we have available, the atomic balance of hydrogen. So we know the hydrogen that gets into the system, that it's only NH, should be equal to the number of moles of water, of hydrogen, and times the stoichiometric relation of water to hydrogen, right? That is two atoms of hydrogen per each molecule of water. And with that, we obtain that the number of moles of hydrogen is 29.8 moles of hydrogen. And that's it. We finished the balance, right? And now we need to answer the questions. So it tells us that what fuel could be, right? To see what fuel could be, we can do a relation of hydrogen to carbon. In this case, if we divide the number of moles of hydrogen by the number of moles of carbon, we're going to find that the relation is around 4, right? 3.97 moles of hydrogen per each mole of carbon. If we put that into a molecular formula, should be CH4, right? Almost, or a multiply of those. Could be C2H that doesn't exist, or C3 or C312, and so on, right? Okay, so because the relation, the most likely compound or fuel that we have is methane, right? Okay, and that's almost it. The only thing we're missing is the excess of oxygen. So let me fill this. Okay, so for the percent of oxygen, we of course the amount of, well, the reactions, right? Because the theoretical oxygen is depends on the reaction, the complete reaction of that fuel. Okay, We can do it with the complete combustion reactions that we have for each element, in this case for carbon and hydrogen. So the complete combustion of carbon is 1 mole of carbon reacts with 1 mole of oxygen to form CO2. And the water is 4 moles of hydrogen react with 1 mole of molecular oxygen to form 2 moles of water, right? So the theoretical amount of oxygen that we need for that particular reaction is the addition of both reactions, right? For carbon, we have 7.5 moles of carbon. Then the relation, the stoichiometric relation, 1 to 1, right? For each mole of carbon, we need 1 mole of oxygen. And then for water again, right? 29.8 moles of hydrogen. And we know the relation is for each 4 moles of hydrogen, we consume 1 mole of oxygen. So with that, we obtain the theoretical amount of oxygen that we need. In this case, 14.95 moles of oxygen. That's the theoretical one. And we know, because we did the balance, that the oxygen that we fed to the system that was in the inlet is 22.4 moles of oxygen, right? And then we only apply the percentage of excess equation, that is the number of moles in the fed minus the number of moles of theoretical oxygen divided by the number of moles of theoretical oxygen. We plug in the data, and we find that we have a 49.8% of excess air. Okay, and that's it, right? That's what this problem. This problem is important for you to understand that you don't need the complete the fuel, the formula of the fuel to solve a problem. Okay, you can obtain the balance through the atomic species. Any questions for this problem?
I have a doubt, teacher. The percent excess air is like a formula. We can always use it.
Yeah. Yeah, that one is this equation that we have. Let me put it in a color. This equation that we have over here is one that you should have found. Sorry, times the 100. That you should have found for the activity of combustion. That is a definition, right? You, with this subtraction, the fed oxygen minus the theoretical oxygen, you're finding how much oxygen you have more than the stoichiometric, right? And then if you divide it by the stoichiometric or the theoretical, you find how much excess it is, right?
Okay.
Any other questions? Yep. Okay. So, well, with that, we finish this class. We will see you on Monday, sorry, to do a couple of things about equilibrium phases in equilibrium. And well, on Thursday we will have the exam. I don't have the date or the schedule right now, because well, we need to have a presential exam, right? So I will let you know through an email when and where, right? Okay. If that is all, see you next week. Have a good weekend, guys.
Thank you, teacher. Bye.
See you later.
Thank you, teacher.
Bye.
Thank you.
You're welcome. See you.